Hello! This is a hand plane and I use it for woodworking. The idea is that this sharp iron runs over the wood to create the surface of a flat plane. If any part of the wood surface rises above our planar surface, the hand plane shaves that part off. You do this over and over again to get your project almost perfectly smooth. But how does this relate to neural networks? Today I want to show you how neural networks incorporate linear transformations to classify data. I'm Matt and I love woodworking. I mean, linear algebra. Neural networks are among the techie buzzwords floating around. Machine learning, artificial intelligence, deep learning, neural networks, these words are everywhere. But what is a neural network? The word neural is included because these networks are inspired by biological neurons, where electrical charges accumulate inside the neuron cell body until they cross a threshold, at which point an action potential is sent down the axon towards other neurons. Similarly, neural networks have units or nodes that receive input and activate when a threshold is reached. However, this is where the similarity ends. Now, biological neurons are way more complicated than the units of a neural network, which are simple enough to be implemented on your computer. In fact, if you've ever multiplied a matrix and a vector, then you've already seen a big part of what neural networks actually do. Before I dig into how these models work, let's set up the classification problem. Suppose you have a data set made up of shopping habits of customers at a clothing store. Each observation in your dataset is a vector, where the entries of each row represent the time spent in the store, the amount of money spent during the visit, and the time of the visit. You also record whether or not the customer bought an item from the monthly promotion. Now, you want to create a mathematical model that will use your data to predict whether future customers will buy the monthly promotion. You also want to test your model to make sure it is reasonably accurate before using it. To do this, you split up your data into two sets, one to build or train the model and one to test it. Okay, now let's build our neural network. Our neural network is going to look like this, and here's how it works. Take an input vector and multiply it by a matrix to get a new vector. Pass each element of this new vector through an activation function that checks if the elements cross some predetermined threshold. Then multiply this activated vector by another matrix and repeat. You can do this as many times as you want. Each time you multiply by a matrix and apply the activation function, you get a layer, and the number of layers gives you the depth. A deep neural network usually just means you have more than one layer. Let's hold up here. What is really going on? Well, when you multiply a vector by a matrix, the resulting vector is exactly the same as if you took the dot product of the rows of the matrix with the input vector. Now, geometrically, this means you are comparing a plane, a flat plane, to the input vector, since the row of the matrix can represent the normal of the plane. When you apply the activation function element-wise to the result, you're really just checking which side of that plane your input data is on. Okay, to compute an output for some input vector, you start with a whole bunch of random intersecting planes. Then, compare the input vectors to these planes. After you've done this for all the layers in your network, you compute a final activation function to determine which category your input vector should be in. The result is almost always wrong. Don't worry too much about it. Remember how I said you started with random planes? Well, to improve your model, you'll need to update these planes based on the result of the first pass of your data through the network. This calls for an algorithm. Generally, we use a variation of something called gradient descent to update the network layers. That's a fairly big topic, so I'll save it for another video. For now, let's just say that gradient descent is a way of updating the entries of matrices in each layer so that we get a more accurate result. Now, once your layers have been updated, you run the input vectors through the network and check the result. It's probably still wrong, but likely better than before. You then do this process over and over and over again, sending input data through the network and updating the layers until your model is accurate enough for your purposes. You can spend quite a while watching your model train. Watching your model train. Once you're satisfied with your model's accuracy on the training set, you run some test vectors through it and see how it does. Now, maybe throughout this video you've asked yourself, how many layers should my network have? Which activation function do I use? How many times do I update the layers? How do I make sure my model generalizes to test data? There are currently no firm answers for any of these questions. Maybe you can find them, because answering these questions and others is necessary to understanding and interpreting neural networks. Help us, students of linear algebra. You're our only hope. I hope this video has cut through some of the hype surrounding neural networks. By the way, those terms I mentioned earlier, deep learning, machine learning, and whatnot, they all fit into a very nice diagram. Looks like this. Linear algebra is everywhere. Keep studying, and as always, keep it linear.